Okay, so Newton's third law. We're going to do the basics today. Right. So when I say basic, meaning understand the law, the most fundamental basic problem of Newton's third law is what we're looking at just today. I have a bunch of videos that I really want to show you guys, but I'll try to show a couple of them, but I definitely won't show all of them. There's a lot of great cartoons, and so that's why I had some in the pre-lesson. And yeah, as you can see, I think it's handicapped there with one. And then the snowball one I just thought was a cute picture, right? Because we've had 10 snow days in the last, I think, was it Doug Kramer said 15 or 12 days of snow in the last 20. So the thing is with Newton's third law is the equation is really not very helpful. As you can see right here in the middle, FA on B equals negative FB on A. It's that idea of action reaction. For every action, there's an equal and opposite reaction. You learned it in middle school, like 8th grade or physical science. But what happens is you cannot use Newton's third law by itself, which really means, as you're going to see, we're going to end up by using Newton's second or first law as the predominant law. But Newton's third law it's more about Newton's third law pertaining to more than one object. So if you look at what we've done the last 6 weeks with Newton's first law and second law, we've only looked at one object, right? A person on an elevator. The person is the object. You're pulling something. The thing you're pulling is the object, and we're looking at the forces acting on that. But now we're looking at two or more objects and how they interact together. And so you have to have more than one object. You could have 3, 4, 5, but we're going to stick to 2. And then once we figure out, oh, this is where Newton's third law fits, you're going to see that we're really back to the second law, usually, or the first law. And here's another little good cartoon from bitstrips.com. Right? So this is the law. Whenever object A exerts a force on object B exerts an equal and opposite force on object A. You learned it. For every action, there's an equal and opposite reaction. Again, that's kind of more the middle school definition of the law. You're not going to be asked to repeat the law on a test for me or an AP test anyway. But one of the nice things, if you learn how to say equations, a lot of times you don't really need to memorize, a law like this. There's very few things in physics that, even regular physics, like I tell them, you have to know Newton's 3 laws, you have to know Archimedes' principle and Bernoulli's principle. That's it. Everything else is pretty much given to you. But even that, if you say this equation in words, when I move my mouse, do you guys see the mouse move on the screen? Okay. I don't know if I had a pointer or not. So if I was to say this in words, object A exerts a force on object B. Object B exerts a force that's equal, opposite in magnitude on object A. And so you pretty much just said what I have in words right there. So then you really don't need to memorize any of the laws anyway. You just have to know how to say equations into words. But as you can see there, that's not a very robust equation. Again, here's how you learned it in middle school. So you see, and I use this as an example. This is a really basic idea, but you got two people on skateboards and they're pushing on each other. Well, the guy on the left is pushing on the guy on the right, and the guy on the right is pushing on the guy on the left. And the force here in the middle, where they're pushing on each other, is the same force, but it's acting on, Isaac Newton is acting a little flamboyant there. But compared to this, that's not a very, if that's accurate at all, right? That's a scary picture. This is the artistic version of it. But so what happens is each one of these guys moves in the other direction because of the unbalancing force from the other person. And then they move with an acceleration that's dependent upon how much their mass is, because the force between them is the same. So a lot of people think in that horse and carriage problem, if you looked at the pre-lesson, which I won't go through it a lot, but is a very famous explanation problem, because a lot of people think the forces just cancel out. Like, well, I push on you, you push on me, that means it adds up to 0 and nothing happens. But you got to remember that the forces are acting on different objects, and that force that I exert on you could be an unbalancing force for you that causes you to then accelerate and move, where it may not be an unbalancing force on me, and because of friction or other forces, and maybe I don't move, right? And so the forces don't cancel out because they're acting on different objects. That is the biggest thing that you have to remember. I will show you this, so we'll see if this even works now, because I don't know when I click on these exactly what is going to happen. Now, this is the well, this is how rockets work. Same idea as a fire extinguisher, except obviously it's going vertically up. And then you have the horse and the cart, which this is the classic physics problem. The horse and the cart. The horse is pulling a carriage on level ground. The horse knows the third law of motion. He's a smart horse. He tells the carriage that he will exert a force forward. Apparently, carriages can talk in this world. And the carriage will exert a force equal to the horse's, but in the opposite direction. Right? So the horse explains, I can't pull the carriage forward because the forces are canceling out. So you see right here where this P is, that's the what we call the Newton's third law pair force. But you have the horse as one object. You have the person in the cart as the other object. But the cart has, if you look at the forces just on the cart in the person, you've got friction down here. So here's even another Newton's third law pair. When you push your foot on the ground to walk forward, the ground pushes you forward because of friction, right? So friction is the force that propels him forward. And so you've got another pair right here. But if this P is bigger than friction, right, then it's going to go forward. And so then same deal here. The horse has got to exert a force on the ground, and it's going to be friction between the hoofs and the ground. And as long as this F is bigger than P, he's going to go forward. And so it's the idea. And so the misconception that people have is they say, well, yes, you're pulling on the carriage and the carriage is pulling on you. So these cancel out and nobody goes anywhere. But again, you have to look at this P with relation to the forces acting on the carriage, and F, the hoof on the ground force, with relation to P just for the horse. And this, I'm not going to show you this. You can always click. I think I had this on here, but the minute physics type of idea, they draw through the idea and explain that. And so that's something that you can look up kind of on your own, so I won't use that time. But this is like 10 slides that kind of go through the whole process. Right, and here, this is what we'll be looking at, as you'll see when you're thinking about Newton's second law. Right, I don't care about the force exerted on you. I'm interested in the force you exert on the cart. You pull the cart, and I guarantee it will move. Right, this horse says, well, how can I do that? Because you're going to pull back on me, right? And this guy thinks, and he keeps talking, right? You push harder than on the ground than the pulling force of friction, and goes forward. And now the horse is upset because he's got to do work, right? And so again, here's another example. I always use this as an example because in my classroom I have, let me see if this works while I'm doing this. You guys see now? You don't see me. You see the classroom, right? Hang on a second while we're doing this. Banging their leg into these desks all the time, and it hurts because it's a fairly heavy table. And so it's that whole idea, well, you run into the table, right? The table exerts a force on you, you exert a force on the table. They're equal forces, just opposite direction, right? And they don't cancel each other out. Usually, There you go. That works. Baseball hits a bat, the bat hits the ball, right? And then I found this video as well that on YouTube where they talk about Newton's third law, but I'm not going to use that because of time. But you can look at it on your own if you're excited about it. But it was a cute little cartoon that they made that deals with baseball because it's almost spring and spring means baseball. One of the things I liked about this slide shows you a force time graph, even though they didn't continue and show you what time is here. But in a collision, if you had two things collide, and this is, we end up by doing this when we do the momentum unit because the impulse momentum theorem is based off Newton's second law. And so that's why we do the momentum unit next, because it's all based off Newton's laws. And then the conservation of momentum is based off the third law. And what we do, or what we would normally do, I'm not sure what we'll do virtually, but we would have collisions. I have these carts and we run them into each other. And then if we use the LabQuest with the force probes, we see this type of graph. And what happens is, so why it's useful is because you see that the time duration, right? So the x-axis is time, this is the force. Whenever there's a collision, okay, whether it's a sports collision, whether it's a car collision, anytime two objects bump into each other, the amount of time for that collision is really small. I always call it the impact time. And we'll talk a lot about that impact time being different than the time that we've been dealing with before. So like when something's falling, right, there's a time for it to fall, but when it hits the ground, that's when it impacts. And it's moving at a certain speed when any molecule of what's falling touches the ground. Well, there's an impact time for it to come to a stop. Impact times are very, very short, but we want them to be bigger if we want the force to be smaller. And so you see the spike. And so what we do is we, taking into the, Newton's third law and conservation of momentum, is we try to make the time duration longer to bring the force down so that we have smaller forces when we have collisions. So this shows you a truck on the train, how the forces are the same, right? One's positive up here, one's negative down here, and the duration of the time is very small. And so what happens is, so this is leading us into the problem solving. We say the force on the truck is equal to the force on the train. Well, if they're the only two objects in our collision, then we know that an unbalanced force equals m times a, right? An unbalanced force equals m times a. Now, the mass of the train is going to be huge compared to the mass of the truck. So that's why I use a little m and a big M. But we know that a smaller mass will have a bigger acceleration, right? And so the truck colliding with the train is going to have a much larger acceleration than the train, which may or may not even have any because it may not unbalance it at all, right? But that's the idea, and that's how we do Newton's third law problems, as you will see. This was a nice, I think I took this from thephysicsclassroom.com. But it's kind of like if you skateboarded, which you guys all probably had at some point. You push on the skateboard, you push on this canoe, and you see that he propels forward and the canoe goes backwards, right? He pushed on the canoe pushed on him. If the canoe doesn't push on him, he can't go forward. And you see the canoe goes backwards, so you know that he pushes on the canoe also. Now, if there was enough resistance force in the water on the canoe, then it might not move. Obviously it would, but if it was on, if it was on your driveway, then it probably wouldn't move because friction would be great enough to keep it from moving, but you would still go forward. So I like that idea of, this little animated picture, being able to talk about or show you that, right? Try to make that analogy to skateboarding, which most of you have all done probably quite a bit. I forgot what time we get out of here now. I got to get used to times again. I'll show you this.
Here we go, folks. The ultimate zero gravity experience.
Look at me! I'm flying like Superman's dog! Race you to the cockpit.
So that was the part of this whole thing that was Newton's third law, which, right, it's kind of gross, but when the thought was that I could do no, shouldn't have done that.
Race you to the cockpit.
There you go. Right, so the gas coming out of their burp is propelling them forward because they're pushing on the gas is pushing.
Folks, it's time for our final run.
No way, I want to go a million more times.
Sorry, boy, you have school tomorrow.
Rich kids don't need school. When I grow up, you can buy an apartment building and make me the super.
With that attitude, you'll never super in one of my buildings. Boy, I am through spoiling you. First thing tomorrow, you're going back to the rotten life you've always enjoyed.
Oh, yeah? If you don't keep splashing the cash, I'm gonna tell Mom that it's thanks to you she made the first bad wedding toast ever.
Blackmail your father in space, will you? Hey.
That's evil burp. A cannon is another great example of Newton's third law. And again, we're going to look at this in terms of conservation momentum. And so you see here, right, there's a cannonball inside the cannon. If you've ever gone to like a Civil War reenactment, which is the only place I can think of where you would see a cannon, unless you watch the Columbus Blue Jackets hockey team, they have a cannon. You go to Osborne City's football game, if they score, they shoot off a little cannon. But the cannon goes backwards, it recoils, right? That idea of recoil, it's recoiling because the cannonball pushes on the cannon, right? Just like the cannon pushes on the cannonball, obviously because of the explosion that causes it all. But the cannonball has a smaller mass, so it's going to have a greater acceleration. The cannon has a very big mass, it has a much smaller acceleration backwards, right? So they each received an equal force. And so again, looking at Newton's second law, because we're causing acceleration, big mass, small acceleration, small mass, big acceleration, the F is the same, right? But that force is an unbalancing force to cause the acceleration for each object. Now looking at this, I love, these are one of my favorite cartoons. They don't show them anymore, but look at these two situations and say to yourself, would this work, right? Hopefully you would look at it and say, there's no way this could work because this is like a motorboat in a tub of water on a little wagon, right? And if he turns it on, yeah, it's going to splash the water around, but how is that going to make him go forward? I used to have the clip to show that. It was linked on YouTube, but it's disappeared and I can't find it again. But this one I do have. So, but here again, this is a very interesting thing because he's got the fan and it's attached to his body. He's on roller skates, but the fan's attached to him as well. So when he turns the fan on, right, the fan is going to go around and it's going to push the air to the left. The air is going to push on the fan to the right. So then the air comes over here and pushes on the sheet to the left, but the sheet's going to push on the air to the right. So you got a bunch of Newton's third law pairs. But here's the problem, is they're all connected to the same object, right? So that he should not be able to go anywhere. But because it's a cartoon, oh, man, I even made this one work. Oh, you know why? Because now I'm not on my laptop. Huh. So as you can see, it works. And it works really well. But, right, Newton's first law, you couldn't make the turn, object of motion wants to continue in motion. Friction was not going to provide him the ability to turn. So what happened was the Mythbusters tested this whole thing out. And so obviously he's going to have a bigger acceleration because he has a smaller mass for the same force, where he has a smaller acceleration because he has a bigger mass. And so using those scooters, you know, from PE class, we're able to do that, and it works decently well. kind of as one of the activities that we would try to do based off Newton's third law. Normally we don't do like a write-up lab on Newton's third law, and we do some of these little activities. So, but this is the most fundamental basic problem that involves Newton's third law. But what you're going to see is the amount of time we spend even discussing Newton's third law is a blink of an eye compared to really doing what we've already been doing. And I thought I had a slide for doing that. So again, we have, there's two situations here. How we solve these is exactly the same. Okay, they look different, but their solution is identical. And I actually had one example typed out in the pre-lesson for each one. So if you didn't look at it and you're trying to do the homework and you're like, I'm not sure, based on what we do here, you can always go back to the pre-lesson. There's a worked out example of each of the two cases. The first case is where you have two boxes. So imagine like you're in your garage and you've got some boxes there, or you have some totes and you got to move them around, but you really don't want to move each one individually. So you kind of push one into the other and then push both of them at the same time. And so this hand is pushing on the blue box to the right. The blue box then pushes into this, I guess, yellow box to the right. And so right here, where these two things are in contact, there's a contact force there that ultimately is, there's a Newton's third law pair. The blue box pushes to the right, the yellow box pushes back to the left on the blue box. So there's that contact force here. But then they're both going to move with the same acceleration. So what we do is we look at the system to find the acceleration, and then we use the individual force diagrams to find the forces, right? So acceleration is always going to be involved in these. I don't even know why I put if, but the acceleration of the system is the same. Both of these things are moving together, so they're going to have the same acceleration, the blue box and the yellow box. So the system analysis is performed to determine the acceleration, and then we do individual object analysis to find the forces, right? Each box is considered its own object. Each box needs a force diagram. There could be more than two, but generally we're going to keep ours at two. There's a good problem. I think I have it for a bell work problem, maybe for tomorrow or next Tuesday, where there's three, but you'll see that when I get to it. Most of the time, it's just going to be two. And again, if you think about the amount of, especially because the AP test is changing, when you have to assess a concept, and you can make it harder and longer with three boxes, but you can do that. You can achieve the same thing to find out if somebody really knows what they're doing, and make the problem shorter and do two boxes. They're going to do two boxes. And so this was another example that I didn't put in the pre-lesson, but essentially it's a worked out example, and I have an example of each of these. But you see here, these are attached by a string and they're not pushed together. All right, so here's the first one I'll do. You got two masses, 5 and 7. You got a 30 Newton force. You're pulling on the 7 kilogram mass to the right. And so you're pulling on this one, but there's an attachment here, a cord of some kind. And so the 7 is going to push on the 5, or pull on the 5 to the right. But the 5 pushes or pulls back on the 7 to the left. We're assuming a frictionless surface, right? If there was friction, then obviously we would do what we just did with Newton's second law and the friction problems. But I'm pretty sure I kept them all frictionless. But we want to know, what is the force of tension in between these, the 5 and the 7, in this cord right here? Oh, good. I did do something correct. So you have two masses. So the first thing you want to do is make a force diagram for each one. Right? So you have a normal. Okay. I don't know why it keeps doing that. All right, let's try this. let's try using the annotate bar with zoom. Let's see if that's more successful. All right, so we have, seems a little too chunky there. Let's try 18. All right, so now what do we have here? We're looking at this guy. This guy is pulling on this to the right? And so there's the force of tension. Now for the heavier one, right? I would make this slightly bigger just because we know the normal force is going to be slightly bigger. And again, I wouldn't take off points because you didn't, but just so you know, if you looked at a multiple choice question and you're like, why is one bigger than the other? It's because it has a bigger mass. So now looking at the horizontal forces are what we care about for all these problems. We're pulling to the right, with a force of 30 newtons. So we'll call that F. We know F is equal to 30. Now, when we pull on the right on this one, it pulls on the 5 to the right, but the 5 pulls back to the left on the 7. And this, is that force. So a lot of times what you'll see is they'll see that done. This, this force is the Newton's third law of pair force. It doesn't cancel out. For the system, it cancels out because they're moving together. But individually, they don't cancel out because this force is the unbalancing force to cause this to move, right? And so here you make your force diagram for each object. And so what you do first is you find, Dakota didn't know what MT stood for yesterday. I obviously like to make fun of her, but it's the total mass, right? And so you add up all the masses in the system. Now, I think you guys can all add 5 plus 7 to get 12 kilograms. So if you just put MT was 12 kilograms, I would be fine with that. But I'm showing you that's where I come up with 12 kilograms. And so what we do is we do the system analysis first. And what we say is that the sum of the forces on the system equal the total mass times the acceleration. So now I'm saying a system. So what that means is we're taking these two individual masses and we're getting rid of them. And we're creating kind of a new problem where we have one mass that we pull to the right with that force of 30 newtons, but has a mass of 12 kilograms, right? This scenario and this scenario is exactly the same because this force is still pulling 12 kilograms. This force doesn't care that it's separated into two boxes. Again, frictionless. And so when I look at this, and I make a force diagram for my system, that's my force diagram. We can solve for this. We can set this force equal to MTA. There is nothing to the left because we're saying there's no friction. So again, this, and I'd said this to a couple people on your homeworks in the last unit, normally there's always going to be a force to the right minus a force to the left. A force up minus a force down always, because the force down is always gravity, right? The only time you're not is if you see there's no force to the left, if it's frictionless. And so what we're going to use is we're going to use this to solve for the acceleration, right? And so now I'm going to plug in my 30 newtons. I'm going to divide that by 12 kilograms. What is that? 15 over 6 is 2.5, right? And so both of these objects are going to have an acceleration of 2.5 meters per second squared, right? So step 1, find the total mass. Step 2, make your system force diagram. Make sure you have all the forces. for 99% of these problems, right, it's just going to be F because we're ignoring friction. Friction equals the total mass times A. We use that to find A. Now, we do the individual analysis. To find the force. If there's only two objects, you only need to do this for one of them. If we had three objects, we would have to do two of these. So here's what we do. Always pick, I'm sorry, my writing is getting worse with this setup. Always pick the object with the least amount of forces. So when I look at object 1 and object 2 has these two forces. Object 1 has just one. So let's use the one on the end. But essentially, whenever you're pulling, it's the one on the end. Whenever you're pushing, it's the one that you're pushing. Or no, sorry, it's the one that's being pushed. So I'm calling this object 1, right? This is object 2. So I'm going to say the sum of the forces on object 1 in the x direction, right, equal m1a. And so I know that this is t, right? It's this equals m1a. Well, we know m1 is 5 kilograms. We know a is 2.5 meters per second squared, which gives me 12.5 newtons. This has to be less than the pulling force, right? Otherwise, it wouldn't move. And so that would be a way to know, hey, I've made a mistake. If this came out to be greater than 30, that's not possible. Questions on that? Now you're going to see it. There's probably, I don't know, there's 3 or 4 problems on here. I'll do 1 or 2 more, whatever we have time for. But you're going to see I'm going to do the same thing over and over and over again. Add the masses together. Set the force equal to the total mass times A so I can find the acceleration of the system. And then go to the individual objects, pick the one that has the least amount of forces, and solve for that tension force or the contact force, depending on what it is. Any questions before I go to the next slide? Clear the drawing. Okay. So here's the other kind, right? So you're over here on the left, you're pushing on box A. You push box A into box B. So now they're touching. There's a contact force in between these two guys. Box A pushes on box B pushes back on box A. Box A has got a mass of 14 kilograms, box B has a mass of 10 kilograms. You're pushing with a force of 8 newtons, right? What is the acceleration of the two boxes? What is the contact force between them? So it's the other kind of situation. Instead of something in between that's a chain or a rope, you've got them in contact. The setup, though, is exactly the same in terms of what we're going to do. So what do we do first is make a force diagram for each normal force, force of gravity. So you're pushing on box A to the right. So there's that FP, they're calling it. I feel like that. Let's make this a little skinnier. So then we come over here, right? And so it's a smaller box, so it's going to have a smaller normal force. Right, so now, this is the only force that's applied, but box A is pushing on box B is pushing back. And so this is the Newton's third law pair force that we need to put in. And so I'll call this C for contact. Okay, but so that's that one, A on B, and this is B on A. Now, this obviously has to be bigger than this in order for the system to move at all. But again, if you saw a multiple choice question and it had force diagrams and you saw them equal, and then you saw one bigger, the one bigger would be the answer because they're using magnitudes of the length of the vector to indicate that. So do this first. Second step, find the total mass, right? A plus B, MT, total mass, 24 kilograms. All right, so now what do? Now I do the sum of the forces in the x direction equal the total mass times the acceleration, right? I'm doing the system analysis to find the acceleration. Well, it's just this FP. When I look at the system, meaning I'm really looking at one big box and not two smaller boxes. That's the only force that's acting on this 24 kilogram box. So it's FP equals the total mass times acceleration. So I take that FP and I simply divide it by the total mass, which was what, 8 newtons divided by 24 kilograms, which is 1/3. Right? Same steps I did last time. Now we come over here and we say, okay, to find the force. Find the one with the least amount of forces acting on it. Well, this has 2. This has 1. Pick this one, right? The sum of the forces on box B in the x direction equals the mass of B times the acceleration. Well, what is the force that's causing box B to move? It is that contact force equals the mass of B times the acceleration we just calculated. So I take the mass of B, which was 10 kilograms. I take its acceleration, right? 3.333 times 10 makes 3.3 newtons, right? And again, it has to be less than the FP force, the applied force of 8 newtons. Now, I want to just show you. So again, you want to make life easy, you want to pick the one that has the least amount of forces. Well, let's just say you pick this one. It still works, right? If I do the sum of the forces on, I'll do it over here, box A, mass of A times acceleration. I simply say FP minus C equals, right, the mass of A times its acceleration. I'm trying to find C, right? So it's simply, if you get it wrong, it's just because you do some bad plussing and minusing, right, adding and subtracting. Because when you solve this for C, it's going to be FP minus M times A. And so I take 8 newtons, right, that was given, minus the mass of A, which was 14 kilograms, times the acceleration of 0.33, right, which is 8 newtons. So obviously that has to be what, 4.7 or 4.666. Do that. 14 times 0.333. Yeah. And I get the same 3.3 newtons. You do not have to do both. You just do one, right? The other one's just simply a check.